The smells of steaks in passageways, the burnt-out end of smoky days. That's T.S. Eliot, one of my favorites. That has nothing to do with the class, but I love that T.S. Eliot. Oh, this yours. Excellent, excellent.
Thank you.
The best. Well, okay. Well, I have, much to my surprise, I've realized that we don't have a lot of time left. So I wanted to finish the DFT and just a little bit of filter design. So I better get moving along, I guess. So last time, since I saw you last week, I have posted the final homework and the final project. Now, I'll say a few words about the project later on. The project, by the way, is due. I've just made it due on the. You can turn it in at the final. You can turn it in before then if you want, but the final, that's sort of it. I can't extend it any further, obviously, or you won't get your grade. So that's your. If you want, you can wait. You can turn it in at the final, but that's about it. The fifth homework is due in well, I guess it's due in another week. Now on the fifth, and then there will be a sixth homework, by the way, which will be some sample problems. So you'll have that, and that's what we will do to finish the class up. Okay, so let me get started. We have a little bit of ground to cover. Last time, we discussed the discrete Fourier transform. We discussed yes, you can see it up there. We discussed the definition of the discrete Fourier transform. And the thing about it is that it's a transform that's discrete in both time and frequency, A, and B, it's only defined over a finite set of data. If you try to compute the transform beyond that, or I should say the inverse transform beyond that, it'll just be periodic extension. So it won't give you any new information. So basically that's it. So the DFT, the frequencies are discrete, and they occur at, as we talked about last time, at the discrete frequencies omega sub k 2 pi equal 2 pi k over n, where n is the length of the transform. And so there are typically n of those frequencies that are computed, and only n. If you, like I said, the same thing with the inverse. If you try to go more than that, they will just be periodic, so they won't give you any new information. So your transform is finite in frequency, and then the inverse transform is also yes, that's what I can do. It's also finite in frequency. It just gives you the original samples back, n samples. Again, you try to compute the inverse DFT with little n greater than, little n greater than 0 or less than, here you go. Greater than n minus 1 or less than 0, just be periodic. So that was the DFT. We identified last time, I discussed some properties of the DFT, related it to finite transform, or well, I should say related to the TFT of a finite data, pretty simple. It's just basically the DTFT evaluated around the unit circle at equally spaced points, either, and that goes for the Z transform too. So we can relate it to other transforms like the Z and the DTFT, but the DFT is distinct, it's different, and it only applies to a finite amount of data, and it is discrete in frequency. So we talked about some of its properties. That's kind of where we ended up last time. I didn't get quite as far as I wanted to, but it is a linear. And like the DTFT, if we have a sequence and we do a linear shift and we take the DTFT, it's equal to e to the minus j omega shift times the DTFT of the original sequence. Well, we have a similar thing with the DFT, but the difference being that instead of a linear shift, if we have a sequence, finite, 0 to n minus 1, and we do a circular shift of that sequence, we discussed that last time, and we take the DFT, then the DFT of a circular shifted version here is also equal to e to the minus 2 pi j k times n naught. N naught is the circular shift over n times x of k. So there are counterparts to the linear shift theorem for DTFT in the DFT, and there it's circular shift. So the DFT basically works on circular shifts of sequences, or it works on the sequence itself. And recall circular shift we discussed last time. There's graphical ways to see it, but basically it's evaluated as, it looks kind of like a linear shift, x of n minus n naught, except that there's the modulo n function. So that takes whatever n minus n naught is, where n naught is the shift, and it moves it into the interval, the mod function moves it into the interval 0 to n minus 1, so that the circular shift keeps it's well defined over the interval 0 to n minus 1. So that's what the circular shift does. You can think of it as taking the input sequence from 0 to n minus 1, just replicating it a bunch of times, 0 to n minus 1, n to 2n minus 1, etc. Just keep repeating it, and then you can do an ordinary shift on that. Or you can use the picture, the mnemonic of a wheel that you turn with the n samples. So that's what the circular shift is. That's pretty much where we ended. We did discuss some symmetry properties of the DFT. For real sequences, there is a complex conjugate, symmetry basically around the middle point. Remember, the DFT samples are 0 to n minus 1. So there's complex conjugate symmetry if the sequence is real, the finite sequence, about the point n over 2. And it includes, and n over 2 is real if n is even. So that kind of catches you up to date. And we ended by discussing or defining a circular convolution. And that's kind of where we ended up last time. And so to repeat, a circular convolution, it's just like a linear convolution. Here it is. Suppose I have two sequences, both finite, x and n, both defined over 0 to n minus 1. Then the circular convolution, again, looks just like a regular linear convolution, except that it has a modulo n in front of it, so that everything with the shifts here, n minus m modulo n, those values are between 0 and n minus 1. Okay? So basically the only difference is between the DTFT and linear shifts is the mod function, which keeps everything cool, keeps it right between 0 and n minus 1. So this is defined to be the circular shift, the circular convolution of two finite length sequences. I could also have put the n minus n mod n on the x of m, I could move these either way around, just like we could for linear convolution. But this is the definition of the circular convolution of x and y, denoted as convolution with a circle, obviously. We were in the midst of discussing some properties. In particular, the one that I had mentioned last time is this. If you let z equal x circularly convolve with y, now again, x and y finite, 0 to n minus 1, and you take the dft of x, little x, and y, you get big X of k, big Y of k as defined. Then the dft of z, you don't have to recompute it, it's just the dft of x times the dft of y. So this is the counterpart of the linear convolution theorem that we saw for DTFTs. Here it's circular convolutions, but the results are analogous. Okay, so that is the now if you look at your homework, the last homework that's due, actually this theorem that I'd mentioned that I didn't prove, this one, that's one of the problems. So you can try it. You don't have to do all the problems, just I think 6 out of 9. But if you want it, you can try it or wait till the solutions come out. So I'll show it to you then. So that kind of brings us up to date. So let's go ahead and keep going. Let's see. Okay. One thing I wanted to point out, if we want to compute the circular convolution of two sequences, it is advantageous to use the DFT, since it can be computed efficiently using the FFT. So here's an example. Now, this again is if we want to do a circular convolution. Filtering, keep in mind, is defined only with linear convolutions, not circular, but we'll come to that in a few minutes. But let's say we did want to do a circular convolution of two sequences to compute z of n. How many operations would that take? Well, you would have to do basically n adds, and for each of those adds you've got to do multiply. So you'd have to do n adds and multiplies, and then you would have to do that for each value of n, which you compute, little n, of the output of this convolution. So that's 0 to n minus 1. So basically on the order of n squared operations would be required. Now, however, if you take the seemingly longer path of DFT-X using an FFT, DFT-Y using an FFT, that's two DFTs, and then take the product and then inverse DFT to get z of n, it sounds like that's a lot more work than just doing this. Well, it turns out, but it's less computationally complex. This is order of n squared. Maybe that doesn't seem like much, but for n getting large, like 100 or 1,000, this is a lot of operations. In fact, n doesn't have to be very large before n squared, even with the biggest, largest, fastest mainframes or desktops today, the n doesn't have to be very large to where this will choke whatever processor you're using. However, with the DFT, let's see what you would do. Well, hang on. Yes. Oh, I don't want to get confused here, guys. Okay. So let's see where you, with the DFT, you would have, now I'm discussing this in a little bit more detail because it relates to part of your last class project. So in any case, so if you were to use a DFT, as I said, you'd have to first DFT-X, DFT-Y, product those two, and then do the inverse DFT. But if you use the FFT, steps 1 through 3, all of them can be done in order of n 3/2, n log n, plus n operations. The plus n is just for the multiplies. You have to do n of those, x times y. But to do all of the DFTs using an FFT algorithm, the complexity grows like n log n as opposed to n squared with the direct approach. And for large n log n is much, much less than the order of n squared operation. So this is typically much, much less than order of n squared for large n. So it turns out it would behoove you to if you were to do a circular convolution, to do those 3 steps. It might seem like a lot, but it turns out for large n they can't be beat. You can do these on most of your standard desktops using MATLAB, but the n squared thing breaks down for large n. So this is the way to go, except for one little thing, and the little thing is this. That's how you would compute the convolution with a circle. Okay? What you'd really like to do, though, is compute the linear convolution using this DFT, this fast FFT technique. Now, unfortunately, in this class, we won't have time to discuss the class of FFT algorithms, but so you'll have to believe me. I appear to be an honest person. That you can do an FFT in order of n log n. If it's what we call a power of 2 FFT, then it would be n times the log 2 of n. So if n were, I don't know, 2 to the 20th, you'd be talking about log to the base 2 of 2 to the 20th is 20. 2 to the 20th is roughly a million, so it'd be 20 million operations. Figure out what that would be if you did it with the direct method n squared. I think you get the idea. But in practice, we're typically not interested in circular convolution. Some applications we are, like with the cyclic prefixes. But generally, we want to do a linear convolution if we're doing filtering, for instance. So the question is, can we use this fast routine to do an ordinary linear convolution? And the answer, of course, is yes. But how is the question. Well, this is where zero padding, the concept of zero padding sequences comes into play. This is one of the first places we use it, where essentially we increase the length of these finite sequences by appending a bunch of zeros. You might say, geez, does that buy you anything to add zeros? I mean, you're not really adding any information. Well, it does in the sense that it will permit you to do to use a fast FFT or fast FFT to do these convolutions. So, and again, the only reason I'm spending any time with this is because it does relate to your second class project. Well, what's coming up does. So here's one way to do it. Suppose you have 2 sequences. They're both finite, but they're different lengths. So one way to do it is to generate what I call zero-padded sequences. I denote those x and y were my original finite sequences of different length. X sub z and y sub z will be my zero-padded sequences. And I will add enough zeros to each sequence so that the length of each sequence is the same, and in fact is equal to length of x, y, zero padded, okay, by just putting zeros at the end. So here's an example. You come to this x sub z of n is x of n for the samples you have, and then after that it's zeros, and I'm zero padding this out to length, basically the sum of the lengths. Well, it's sum of the lengths minus 1. It's out to length n plus m minus 1. So both of those sequences will be zero padded to a common length, which is more or less the sum of the lengths of each sequence. So that's the first step here. Now let's see what we do next. Let's see. Oh, okay. And then these are just some properties of the zero-padded sequences. Basically, it turns out because you've zero-padded, extended the length, it turns out that the how shall I say, the shifted value, y sub z of n minus m, for instance, modulo its length, n plus m minus 1. Now that's the new length. It's just equal to y of n minus m. So in other words, what you've done is you've made these circular shifts over the longer length of each sequence the same as ordinary shifts. So that's a cute little trick. So what that means is that if you want to do the ordinary linear convolution, you write it like this. Now I'm summing over the x of m is the x sequence, and that has length 0 to n minus 1, and then I'm going to delay the y sequence, y of n minus m, or I could have, turn it around where I'm delaying x, okay, so either way, but I just wrote it like this. Now it turns out that, interestingly, y of n minus m, it turns out is equal to the 0 padded circular shifted sequence n minus m modulo n plus m minus 1. By the way, if you're interested in the details, I'll show you where I have some notes at the end of this, which are just kind of like an appendix, which shows you these proofs in more detail, and they're typewritten, so that's nice. So in any case, proof, like I said, proof at the end of these notes. If you believe that, then you'll be willing to go a step further. X of m for m equals 0 to n minus 1 is the same as x sub z of m, and you can extend the summation to 0 to n plus m minus 2. Why? Because you've 0 padded out all those samples. So now look what you have. You have a convolution. There's the modulo property of two of these sequences, both of length n plus m minus 1, and that is equal to the circular convolution of the 0 padded sequences. So basically what you've done is you've taken an ordinary convolution and converted it into a circular convolution by 0 padding the sequences out to n plus m minus 1. And now you can apply the steps to this circular convolution. And so what you would get, thus to compute x, the linear convolution of x and y, via the DFT-FFT technique, you'd 0 pad both to a common length, would have to be greater than or equal to n plus m minus 1. Actually, it could be greater than that, but it has to be at least that large. You DFT both sequences, okay? You would multiply the DFTs together, and then you would take the inverse DFT. And the inverse DFT, this would give you z of n. Now this will be of length n plus m minus 1, so all you do is take the first m, what did I call m? What did I say that was? You take the first n samples to n less than or equal to n minus 1. And that, voila, that will give you your linear convolution. So it's a cute little trick. Furthermore, you know that the computation, if you use the FFT, is of order L log base 2 of L plus L. Okay? So computationally efficient. That's a very efficient way. If you had to do a linear convolution. Now, we do want to do linear convolutions if, for instance, we are filtering. Suppose we want to filter an infinite sequence, x of n, I mean, it just goes on and on, with an FIR filter. And as you will see, surprisingly, the longer the FIR filter, the better the advantage you get of using this FFT. So this technique is an important way to do filtering, FIR filtering with long filters. And I will exclamation that. This is a very powerful technique. And you will see when you do the second class project, there are like 3 mini projects part of that, but there's one that actually you will get a chance to compare FIR filtering using this technique, using the MATLAB function, filter function, and using the direct function. And this beats the socks off of any of those other techniques, including, yes, the filter function in MATLAB. This destroys it for large FIR filters. And the idea here is based on something called, what is this called? Hang on. Overlap add method. This is called the overlap add method. And the basic idea is that you take this infinite sequence you're trying to filter, and you more or less break it up into non-overlapping segments. Just give me a sec here. I want to make sure I get the right reference. Yes. Okay, I want to make sure I get that reference. So the basic idea is that, like I said, you take the you take your input and you break it up into overlapping segments. So what we're going to do is, by the way, I should have pointed out, if you do this the direct method, even if you use the MATLAB filter function, what is the computational load? Well, again, suppose the filter, the FIR filter, is of length m samples, then you have to do, once again, you have to do m multiplies and adds every sampling clock, see? Every value of tick of n, you have to do m multiplies and m adds. That adds up, and especially it becomes very difficult as m increases when you have a finite clock frequency. You know, this thing adds up very quickly. It can get into gigaflops very, very fast. So m adds and multiplies per output data point for the direct method. Keep that number in mind. We'll come back to it in just a moment. An alternative technique is the, and I want to make sure I get the right reference. Yes. Is something called the overlap and add technique. And this, a good reference for this is Mitra, section 5.10. You will get a chance, I mean, in terms of, would you see here, that's at least in the 4th edition. Will you see a problem on this on the exam? Realistically, no, because you don't have a computer. So, but this does pop up in the project. The project gives you a nice chance to use this, and again, like I said, you will be absolutely amazed at the results of that. So, that's important to give you some idea of the power of this method. Anyway, this is all in Chapter 5 of Mitra. The basic idea is that you partition this infinitely long input sequence, you partition it into non-overlapping segments, subsegments of length L, okay? So that's basically what x of k is. X of k is the kth segment, and it's just defined to be this. X of k is x of n for 0 less than or equal, I'm sorry, for k L less than or equal to n less than or equal to k at 1 plus L minus 1. So each segment is of length L, and 0 outside of that, so they're non-overlapping. Call that x of k of n, and then you find that x of n, since they're non-overlapping, is just the infinite sum, x of k of n, okay? So that's exactly what it gives you. So now let's look at the convolution, the filtering operation. The filtering operation is equal, looks like y of n is equal to h convolved with x, but that's also equal to h convolved with summation k, x of k of n. And since the convolution is linear, I can take that inside. So that's this, k of h convolved with x of k of n. Now, the beauty of this is h is finite. It's an FIR filter. X of k is finite. So now you have two finite sequences that you're going to do a linear convolution on. But I want to do it very, very fast using an FFT, so now we know how to do that. Zero pad these two, basically, DFT each one, the zero padded, multiply inverse DFT. That's kind of what what we're doing here with this overlap add technique. Now we can use the DFT, FFT to compute h convolved with x sub k. And so what we will do is do this. We will segment x into the x sub k. We will zero pad h and x sub k to a length equal to m plus l minus 1. M is assumed to be the length of the FIR filter. L is assumed to be the length of the segment, and called it h sub z and x sub k sub z. So that's the subscript z just denotes zero padded. DT, FFT, both of these finite sequences multiply inverse DFT. And once you've done that, then you reconstruct y of n by sequentially adding segments. Can't beat that. The only little tricky part that you have to keep in mind is that you have to think about when I do the DFT, when I multiply and then I do the inverse DFT, just a second, sorry. Then when I do the inverse DFT will be of length, yes. So when I do the inverse DFT, this will be of length m plus l minus 1. Now the question will come, which part of that do you take for that? Remember, the segment that you have is only L. So you want to replace the L segment with h convolved with x sub k with an L length segment. So you're going to have some overlap. But if you look at Mitra, figure 5.14 in the fourth edition, let me hope this works. I don't know what. Oh, this is the fourth edition. All right. So if you look at 5.14, this is a case where one picture is worth 1,000 words. Should have had this bookmarked, but what the hell. 5.14. Good grief. Has Mitra run out? Oh, there it is. So there is the little picture that he has. This is figure 5.14. This top one, well, that's just the original sequence, x of n. And here he's taken and broken these and broken into sub sequences of length. It looks like 7. Looks like it goes 0 to. I'm sorry, 0, 1, yeah, 7, I guess, yeah, 3, 7, got to check that. So he's broken it into non-overlapping segments of length 7, and then he defines y naught, yes, y, right, y sub, y sub k of m is, I don't know if you can read that, it's just what I was calling, it's h of n convolved with x sub m of n, okay? That's why, or h of n convolved with x sub k of n, okay? So that's what this is. And again, he's computing that using the circular convolution, the zero padding technique. And the problem is, when he does that convolution, he gets a length. Well, in this case, what is his filter length? 5.14. The filter length is h of n is of length m, and length m, and I'm not sure. Figure 5 shows length 7 and equals 7 segments. Oh, and m is 5. Okay, so when he convolves each of these segments with h is a length 5. So the total length will be 7 plus 5, 12. Minus 1 is 11. So here's is 11 points. Now the question is, what do you do with these overlap regions? And in this technique, which is called the overlap and add. You take these overlap regions and actually add them up. Anyway, he goes on with the thing. Now, I think in the class project, we will be doing that or the overlap save technique. Maybe it is overlap save. But in any case, that's the basic idea without going into details. We don't really have time to go into details. But you'll get a chance to try it out on a real, on some real data or data that you generated in your last class project. But anyway, like I said, this is in Mitra, Chapter 5, Section 5.10.3. So please take a look. And it's pretty straightforward in the class. I give you the code to do it. But you'll probably want to get a little, kind of take a look a little bit deeper into the code to try and see what's going on. But even if you don't do that, that's not required, because since I give you the code, what I want you to do, though, is compare the computation times so that you will be truly amazed. So anyway, that's the overlap save technique. One thing I didn't mention was how do you choose the length of those subsegments? The length of the FIR filter, well, that's whatever the FIR filter is. But what about the length of the subsequence? Is it better to make it equal to the length of the FIR filter, smaller, larger? What I did was, one issue is whatever you choose it, you have to wait, as you will see, L samples before you get the first valid filter outputs, and that's latency. That may be an issue or not. It's not, certainly not in the project. But on the other hand, what you will find is that as L increases up to a certain limit, you will get a better computational advantage using this technique. And what I compute is the average number of computations per output. With the direct method of doing the linear convolution, that's basically M operations, M computations per output, where M is the length of the filter. But what I did was I computed an average number of computations per output using the FFT technique, and I've plotted or tabulated those. Basically, I've tabulated those. Here's my here's the calculations, and I've made a table assuming a 100 point or 100 coefficient FIR filter, and I've done this average computation per output sample, the smaller the better, as a function of that length of the subsegment. And now keep in mind that in all cases using the direct method, it's M calculate or M operations multiplies adds per output sample point. So that's always the same, obviously. But with this FFT, IFFT breaking it into segments of length L, look what happens. If you pick L equal to 29, you find that you roughly reduce the computational load by half over just the direct brute force technique. If you increase L to 157, now you have a larger subsegment length than your filter. Then you further reduce it to roughly a computational load of about a quarter of what it would be with the direct. When I go all the way up to almost 2,000, I find that I'm down below a quarter. Above that, it doesn't really help very much. So it's like I said, it's quite beneficial, and you will be amazed when you see what times you get. What times you get when you use the overlap save technique in the second class project. So, and that configuration for the second class project is a little bit different than what I showed here. I'm just trying to give you kind of a rough idea. Okay, that's it for this part of the DFT. And by the way, these are the supplementary notes I have at the end, which kind of fills in, dots the I's, crosses the T's for the circular convolution stuff that I mentioned earlier. And then this is the circular convolution, the circular shift, etc. I mentioned that last time. So in any case, that is just for your background. Like I said, you won't see anything on this on a final or anything, but it will come into play. You might find this background useful as you do your second class project. And again, the second class project, very, very interesting. Okay, that's that. Now, so that concludes part one of the DFT. That kind of gives you an idea of definition of the DFT, some of its general properties, some tricks in using it for convolutions, and for even for FIR filtering. So that's very helpful. But here's the deal. If you were to compute the DFT, and like I said, in MATLAB uses what is called the FFT function, FFT of x, where x is your array of input samples of length n. No real restriction on n, but it turns out certain values of n, the FFT is a lot faster than other values of n. For instance, if n were a very, very large prime number, I did that example once, the FFT would be very, very slow. You can also do this if you want. Maybe your X array is I don't know, 100 million points or something, whatever your computer can handle, but you only want to FFT a portion of that, then you can also do this. Okay? N, where n is the length of the filter, or the length of the sequence you want to transform. And when it does that, it'll take the first n points and do an FFT of that. So you can do an FFT either way, but it turns out that you can look at the FFT help. I don't think they have much. They have a very powerful FFT, and it works with a large range of values of n. But those n's, which are like powers of 2, powers of 3, for instance, or a mix, power of 2 times some power of 3, say, those transforms go much, much quicker. The FFT algorithms they have are very quick, depending on the value of n. But in any case, there is no DFT function in MATLAB. FFT is all they have. So what I want to do in part 2 is teach you how to use the DFT. So if you did take a sequence of data and you loaded it into MATLAB and you took an FFT of that data, I want you to be able to interpret the results of that. You know, what does it mean? How does it relate to a DTFT if I had an infinite amount of data? You know, how do I interpret? Because when you do an FFT and you get out, let's call this x, or we'll call that x, the length of x is the same thing as n, or the length of little x, the input. So that's all you get. You just get these n values. So the question is, how do I interpret those n values? What do they tell me about the sequence, the spectrum of the sequence? How can I relate it to the DTFT? So that's what this part 2 is about. So there are two important topics which I would like to summarize: relation of the DFT to the continuous and the discrete time Fourier transforms, and also I want to mention a little bit more about zero padding. But the main thing is this kind of interpretation. So if you want to know about this, this is in Mitra. He discusses this in section 5.11.1. It looks like the 4th edition. He discusses this a little bit. I'm curious now. What is in? First of all, why 5.11? I mean, that says he's doing a lot of stuff. Oh yeah. Okay. Yeah. Chapter 5 of Mitra is where he actually this is the 4th edition I have here. Chapter 5 of Mitra is where he discusses the DFT. He calls it finite length transforms. And if you look at section 5.11, that's actually 5.10 is the linear convolution using the DFT. That's what I just mentioned briefly. And 5.11 is, he discusses a little more of applying the DFT to spectrum analysis, which is what I'm going to talk about here. But it's just a short section, so you don't really get too much of the flavor of that. So I decided to expand it a little bit here. So given that there's a lot of ground to cover, we will get started here. So that's the section in Mitra. So let's go back to, let's say I had continuous time waveform. I guess I'm calling it x sub a of t. I'm not going to change that to x sub c of t. And what we're going to do is we're going to take our, you can change the little a's out to x sub c of t, and we're going to sample it as before, and we're going to take x of n, and we're going to compute a spectrum here. We're going to compute that's a continuous Fourier transform spectrum here. We're going to compute a DTFT here, assuming that we have all the points from minus infinity from the beginning of time to the future. We have all the points x of n, and so we're going to do a DTFT here, x sub e to the j omega, summation n equal minus infinity to infinity, x sub n times, you know the story, e to the minus j omega n, and then we're going to capture just capital N points of this, and we're going to do a DFT. So that's DTFT, we're going to do a CFT out here, and then ultimately we're going to do a DTFT with just n points. Okay? N equals 0 to n minus 1, a finite length transform, x sub n times e to the minus j omega sub k times n. Okay? So we will do all of them. And I want to be able to figure out, if I did a continuous Fourier transform here, that probably gives you the most information. How would that relate to a DTFT? Actually, we already know the answer to that. We learned that in sampling. But then, if there's no aliasing, we know exactly how that relationship is. I summarize it here. But then the question is, when you do the DTFT and you do a DFT, how do those relate? How can I know how to interpret the DTFT. That gives me frequencies between minus pi and pi. What about this DFT? It just gives me values 0 to n minus 1. How do I interpret those? So that is what this is about. So first of all, the relationship between the DTFT and the continuous Fourier transform, I'm not going to change this, it just looks like this. This is what we learned in sampling. X sub e to the j omega is a scaled version and of the continuous Fourier transform, frequency scaled. So x sub e to the j omega is 1 over t times x sub continuous, or x sub a of omega over t, and that's minus pi to pi, and this assumes no aliasing. Obviously, if you have aliasing, then you get overlap of the images. And then, of course, it repeats, right? Remember, in the case of no aliasing, the images do not overlap. So you get this, dong, dong, and then you get this, and then so on, just like you would expect for a DTFT. 0, 2 pi, etc., 4 pi, okay? And on the negative side. So that's exactly what you get. So basically, you don't lose a lot of information in going from the continuous, as we know. You don't lose a lot in information from going to the continuous to the discrete time, provided there's no aliasing. Okay. Okay, but the question is, okay, that's fine, but how do we relate the DT? Okay, so I got that. So the DTFT tells me really all the information I want to know about the continuous time signal, provided there's no aliasing. Now I'm going to select n values, contiguous values, x of n from n equals 0 to n minus 1. I'm going to take a DFT of those values. Now my question is, how do I interpret the DFT, or with MATLAB, the FFT, of that sequence of finite data? We're going to get n values back. How are they going to relate to the DTFT? Okay, so that's the big question. So, I hope I have, yes I do. Okay, that's good. Basically, instead of, yes, here's the bottom line. It turns out that when you do a DFT, first of all, can you relate it to the DTFT? Yes, you can. And it's kind of a weird way, but you can do it. And here's how you do it. Now, I don't know if this is actually in Mitra in that chapter or not. So this is good stuff. This is good applied stuff. So when I take a DFT of my finite sequence, it turns out it's equivalent to, so what I'm saying is it's equivalent to x sub w of e to the j omega from omega evaluated at omega equal 2 pi k over n, where k goes from 0, I'm writing it down, to n minus 1, and where x sub w, the same I'm calling x sub w is, of e to the j omega, is equal, in the frequency domain, the convolution of x of e to the j omega convolved with w of e to the j omega. Now, and here's the actual, this is in terms of an integral, right? 1 over 2 pi, integral minus pi to pi, blah, 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 blah. It's right here, actually. Okay? So that's how x of k is related, the DFT is related to the DTFT. I think one year when I taught this, I was trying to cover all this, so I just said that, moved right ahead, and I don't know if anybody understood exactly this. If this is clear, what I just wrote down to anybody, right now, with all I've said, you probably don't need to be in the class. You've obviously had DSP. It wouldn't be clear to me. So let's back off and kind of go a little bit more slowly on this. And again, you can copy this if you want, or you can wait till I will scan it, and you will see it scanned in the DEN documents. Don't forget. Okay, what was I just saying about this x sub w, and where'd that come from, and why is all of that true? So let's start going step by step on this. Okay, just start at the beginning. So here is the definition, right, of the DFT. We'll go take it nice and slow. Sub k of n. This is what we're calling x of k. We are defining omega sub k equals 2 pi k over n, and 0 is less than or equal to k. It's less than or equal to n minus 1. Okay? Haven't done anything. I'm just following the very definition. Okay? Now, here's the key. This is the key. This is why this thing worked out. I claim to you this is equal to the infinite sum. That's right, I said infinite. Minus infinity to infinity of x of n times e to the minus j omega sub k n. I know you're thinking, I thought we didn't know what x of, what are you assuming? It's 0 or something? Times, I wasn't finished, w of n, okay? You think those two are, these two have to be the same. Now you think, what does that mean? Well, wait till I define w of n, and then I think you will agree. I will define w of n to be 1, 0 less than or equal to n, less than or equal to n minus 1, and 0 otherwise. Now, do you believe it? Probably. Kind of makes sense. Okay, sure. So these two are the same, provided w is defined to be this. This w of n, by the way, is also called a rectangular window function, as opposed to other types of window functions, which we use when we use the DFT. But this is called a rectangular window. Basically, it just sifts out the n samples, and whatever x of n is outside of that, we don't know. Well, I guess we do, because we've sampled the continuous input with infinitely long, with an a to d. But for purposes of this, we just know it from 0 to n minus 1. So we can rewrite it as an infinite dtft from minus infinity to infinity when we multiply it by the window function. So this here, this guy here, I digress, let me continue. That's equal to dtft, right, of x of n times w of n, but restricted to the frequencies omega equals omega sub k. Okay, so that's basically it. Done. That is the DTFT. And if you remember one of the results of the DTFT, I don't think we actually proved it, but when we were talking about DTFT at the beginning of the course, one of the properties was that the DTFT of the product in the time domain is the convolution of the DTFTs in the frequency domain. So this worked out to be this, okay, minus pi to pi. And this, my friends, is how we got that thing that I was calling x sub w, okay, w of e to the j omega, minus omega prime. Well, you get the idea. D omega prime. So this is equal to, I ran out of space, sorry about that, that's a mess, x convolved with capital W in the frequency domain. And you know that convolution, this integral? That's what I'm calling, by the way, x sub w of e to the j omega. Okay? So again, x sub w of e to the j omega, let me go write a little bit more. So again, x sub w, here I'll write it where I won't run out of room, of e to the j omega. I'm defining to be that convolution, x convolved with w, which is equal to 1 over 2 pi times integral minus pi to pi, in case there was any confusion with that previous one that I ran out of space on. W of e to the j times omega minus omega prime d omega prime. Okay? And that follows from, all I did was I introduced this window function, and I noted if I did an infinite DTFT, the finite DFT, I could write it like an infinitely long DTFT if I introduced this window function, which I call the rectangular window function. And then all I do is use the property of DTFTs, that the DTFT of the product in the time domain is the convolution of the DTFTs in the frequency domain. So that is where that seemingly strange formula comes from. And now, let me go a step further. So what is W of e to the j omega? Well, x is the DTFT of x of n. W is the DTFT of that window function. So that's going to look like this, right? 0 to n minus 1, e to the minus j omega n, right? Because it's all rectangular. Well, it's times w of n, but that's just 1. So that's summation n equals 0 to n minus 1. And guess what we can use? We can use the geometric sum formula. This is like summation n z to the n, where z is equal to e to the minus j omega. And when we use the geometric sum formula, you find that w is equal to e to the minus j omega n minus 1 over 2. And if this formula looks funny to you, you should sit down and work it out using that sum formula. Okay? And I just manipulated the thing. That was 1 minus c to the n over 1 minus c. Remember? C to the n divided by 1 minus c. So substitute in this, you should get this result, which is sine omega n over 2 divided by sine omega over 2. So that is what the DTFT of the rectangular window function looks like. I've just simplified it, but that's reduced it. So now we have that, putting it together, x sub w of e to the j omega is equal to the dtft of x of n times w of n, which is equal to the convolution in the frequency domain of the dtft of x and the dtft of w, which is this sinc function type function, e to the j omega equals the, what do I call that? I call that x sub w of e to the j omega. In other words, x sub w is just, it's basically the DTFT of the windowed sequence, of the rectangularly windowed. So you're almost done. The only thing left, and this is the simple part, the DFT, finally, is just what I call x sub k, and I know I call this DTFT x, but anyway. The DFT is equal to then x sub w of e to the j omega evaluated at omega equals omega sub k equals 2 pi k over n, and for k between 0 and n minus 1. There it is. So I just related the DFT to the DTFT. Now, you want to get a little more insight into this, which we'll talk about in just a moment, but that's the mathematics, okay? That's the mathematics. And if you look at my notes, hopefully, what am I doing? Okay. So if you look at my notes, you will see that's very succinctly what I wrote down here. X of k, the DFT of x of n is this x sub w of e to the j omega, evaluated omega equal 2 pi k over n. So now you get a little bit better understanding of where this formula seemingly came from. And you also get a better understanding of what the DTFT of w is. Basically, it's what I just said, e to the minus, or is it e to the minus j omega n minus 1 over t. It's a sine function. If I took the magnitude of e to the j omega, that would equal the sine magnitude of the sinc function. One of the problems in homework number 5 is to examine the properties, this optional problem. You only have to do 6 out of the 9, but anyway. But you'll see the solutions to all of them, so you can see what I did. Okay, so that is that. So I say, as kind of a mnemonic or a name, I call, so how is the DFT related to the DFT? I say that the DFT is a blurred and sampled version of the DTFT. Now, where did I come up with that? What do I mean by blurred? When I say blurred, let's see. Oh, here, this is the best place to show it. What I mean by blurred is that the when you compute the DFT, well, first of all, what do I mean by sampled? I mean frequency sampled. You take this x sub w of e to the j omega and you sample it at discrete frequencies 2 pi k over n. Okay, so that's what I mean by sampled in the frequency. But what is this x sub w? How's that related to the DTFT? Well, it relates to this convolution of x in the frequency domain. And you know what convolution does? Here's the convolution. What it does is when you do this convolution, it kind of, this w against w, it tends to blur things, you know. In other words, suppose w of e to the j omega went to a delta function. Okay? If it went to a delta function, then x sub w would equal x. Okay? There would be no, quote, blurring. But blurring means just smoothing this DTFT in the frequency domain. And what do you smooth it with? The DTFT of the rectangular window function, which, as we said, is a sinc function. Okay? So this does the blurring, this does the sampling. So that's what I mean by blurred and sample. Here, let's do a picture example. Here's a picture example. Suppose, just for the heck of it, my DTFT looked like this, and it was repeated every 2 pi, and there was no overlap. Okay, pi minus pi. Okay, so this would be some spectrum, which would be with no aliasing. Okay, so that's my basically this is my DTFT. Now let's plot underneath that the magnitude of the DTFT of this blurring function, namely the DTFT of my rectangular window function. What's that look like? Well, it's kind of like a sinc pattern. It turns out what it looks like is it's a peak. The first null occurs exactly at omega equal 2 pi over n. The second null occurs at frequency omega equal 4 pi over n. So this function has zeros at omega sub k equals 2 pi k over n, which you can see. Because when you have 2 pi, if you substitute 2 pi k over n into sine of omega n over 2, the n's get canceled. You get basically sine omega k, sine pi k, and for any value of k, those are 0. In fact, they're also 0 when k is equal to 0, but then it's canceled out by, well, you get 2 zeros, so you have to use this L'Hopital's rule. But in any case, away from omega equals 0, you get nulls. So it looks like this little sinc function. And of course, when omega is equal to 2 pi, it'll come back and it'll be a repeat. We'll do that over and over again. So you're going to take, in this case, this lumpy function for the DTFT, you're going to convolve it in the frequency domain with a little less lumpier function, but still has some lumps. And you're going to take this, and you're going to, you know how you do the convolution, right? You take this function, multiply it by this, and integrate, okay? And then you move this over a little bit, multiply it by the same function, and integrate. And integrate and integrate. And the output of those integrals is the resulting blurring function, or the convolution in the frequency domain. Now, you can see that if this thing became smaller and smaller, in other words, if the width of this became smaller, in other words, if n increased, and this went to a little spike, then when you did the multiplying and you integrate, you would just end up with this. In other words, very little blurring. But for finite n, this has a finite width. And just a little look ahead, by the way, this width here, or this region from minus 2 pi over, that's the main lobe. We'll come back to this later. And these little guys here, those are called the side lobes of this window function. Okay? So basically, for a finite n, the main lobe will have some main lobe width to it, and you truly will blur out this image. And so if you did this convolution, you might end up with something like this, where before, this is just an example, we'll have better examples later on, where before you had, you know, the DTFT was a finite bandwidth signal. After you get done with the convolution in the frequency domain, that'll tend to blur out those edges. Okay, so you might end up with something like this, and now you're not done yet. You're almost done, but not quite. Now you have to sample it. Okay, now if you look at this and you say, okay, I'm going to sample it in the frequency domain, so I'll get a sample here, 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 and so on over here. So those will be my n samples. Wrong. The problem in using the DFT, the good news with the DFT is you can compute it very efficiently. The bad news is it does not give you the frequencies where you think you should have frequencies. What it gives you when you do the DFT is you don't get any samples. You get all these samples. See? That's what you get. You get these samples. You don't even get the 2 pi. You get the 2 pi times n minus 1 over n. Okay? You do get the 0th sample, but you get the rest of them are these samples. Now, if you're going to do a DFT of, say, a signal that had that spectrum, you would say, well, it looks like that's a nice notch there right at make equals 0. That is not correct. It is not a notch at a make equals 0. In fact, it's a low-pass spectrum. That's the low-pass cutoff. This is just the repeat of the image which would normally occur over negative pi to 0, see? Takes you a little bit of, so can you do the DFT on MATLAB? Sure, it's no problem, just do FFT of x. But when you do it, will you know what you got? Now, that takes a little more work. So hopefully this will give you a better idea. And we'll have more examples in just a few moments. So anyway, that's the basic idea. Note, spectral blurring, how much this thing is blurred. See, this is just a cartoon, basically. But here I showed it, edges were finite here and sharp, being blurred out to here. Better examples are with sine waves, but we'll come to that in a moment. But anyway, the spectral blurring depends on the main lobe width and the side lobe attenuation. So basically what happens is when you do the convolution, you multiply this times your original, you integrate, and you output. Then you move this over. Well, you're going to keep moving it over until the main lobe is going to get outside of the edge of the spectrum. But you know what? You're still going to get something because then you'll be in the side lobe region. So no matter how far you move this over, you're going to get some contribution when you do that integral, either from the main lobe and whatever little side lobe, well, the main lobe will dominate, or from just the side lobes. So the amount of spectral blurring that you get, it will depend on the main lobe width and the side lobe attenuation. And it turns out that with the rectangular window, you can decrease the main lobe width, but these side lobes will always be there. And you can decrease the main lobe width by increasing n, but the side lobe levels will always be the same, as it turns out, which gives rise to different types of windows, non-rectangular. But again, we'll come to that later on. And so here's a little picture that I drew for you. This is a general picture. For a general window, this typically the null-to-null width. That's your main lobe width. And the level of the side lobes relative to the peak value, that distance here, that's called the side lobe attenuation. And typically people compute that in dB. So you compute your magnitude of frequency response to the window function, look at your peak, look at your side lobe, take, I guess it would be 20 log of that. That will be your side lobe attenuation level. Generally, the smaller the side lobe, the better. The narrower the main lobe width, the better, the less blurring. But the problem is, as we'll talk about a little bit later on, there's a trade-off. If you want a small side lobe, you want to get rid of these guys, the main lobe width increases. If you want a tiny main lobe, side lobe levels will generally come up. So we'll talk about that later. Ideally, what you would want as n goes to infinity is you want w to be a delta function, and blurring is eliminated. So, interesting stuff, some of which we will come back to. So that's one comment. In general, the DFT provides a sampled and blurred spectral estimate of the original analog or continuous Fourier transform. Okay. Just kind of a quick little note on frequencies. Oh, wait a minute. I have something here, something real quick. Hang on. Make sure I get all these goodies. Okay. Give me one moment here. Sorry about the flurry. Well, all right. Well, trying to see here, should I? Well, all right. What the heck? Let me do an aside here. An aside. This is a MATLAB. Since you're going to need to use this a little bit on the last class project, a little bit. But in general, you would start, so these are the steps of doing the DFT with MATLAB. I mean, it's pretty straightforward. You start with one given an array of data points, x of n, okay, you start with that, 0 less than or equal to n less than or equal to n minus 1, and then 2, you put this into an array, I will call it x, and it will be defined to be x of 0, x of 1, dot, 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 x of n minus 1. So that would be your array of n samples. Well, you probably want to do that. And then 3 is just simply y equal FFT of x. And that's your output. That is the MATLAB DFT operation. Y, if we look at the output, is equal to the array. Now this will be created for you, but if you look at it, you will get y of 0, y of 1, this will be an array, and dot, 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 y of n minus 1, okay? That will correspond to the frequency omega naught equals 0. So if you're wondering, my first element in array, what frequency does that correspond to? That corresponds in the spectrum to omega naught equals 0. This corresponds to omega 1 equals 2 pi over n. So like I said, this is going all the way out to omega sub n minus 1 equals 2 pi n minus 1 divided by n. Okay? So that's what the MATLAB would give you. If you wanted to plot this, you could do that many different ways. I'll show you a couple. You do this, plot. If you did plot, and you wanted to relate it back to what were the class notes, then you might do it like this, or you would want to do it like this. See? See, I'm trying to see. I don't know what that was. Yeah, you would probably want to do this. See, when you do the plot, this will create the x-axis actually starting at 0. See, in MATLAB, there is no 0 index. I don't know why they don't do it. They never have. There is no 0 index. Your first element of the array is number 1. But we know that number 1, that element, really corresponds to the 0th frequency. Now, if you were just to plot the absolute value of y, on your x-axis would be 1, 2, 3, 4, 5. Maybe a little misleading. So if you really want to make it cool, just like you would get with the notes, you could use this. This automatically sets the x-axis to 0 to n minus 1. So you know that the first point on that plot will be the omega equals 0 point, etc. What else? My MATLAB aside. Let's see. Oh, yeah, I do want to point this out. Might as well point this out, too, while we're at it, and we can come back to that. Now, there's another step you could introduce after you plotted it like that. Let's say you don't like plotting 0 to 2 pi. Well, MATLAB has a nifty little built-in function. It's called FFT shift. And if you've never used it, haven't seen it, I encourage you to learn about it. In fact, I will define it right here. And I will suppose that n is even. There's a similar thing if n is odd. Then, what does y1 look like? Check this out. y1 looks like y of n over 2, y of n over 2 minus 1, dot, 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 y of n minus 1, and then y of 0, y of 1, dot, 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 out to, I ran out of space again, y of n over 2 minus 1. If you count up, there's n points. But what this does is this basic, and we'll see this later, this now puts it into what I call a natural ordering. It turns out this point here is omega equals 0. But as we will see in just a moment, or in a little bit, this point actually corresponds to omega equal minus 2 pi over n. Pretty cool. This point corresponds to omega equal 2 pi over n. And so out here, this actually corresponds to omega minus pi, and this corresponds to omega almost equal to pi. See? So the FFT shift is a very, very useful function. It converts that 0 to 2 pi business. So what it does is it converts this plot from 0 to 2 pi. It takes this piece, effectively cuts it back here, and now makes it between minus pi to pi. So what you can do, if you want, is you can plot now, you can plot minus n over 2, again this is if it's n is even, there's a similar thing if n is odd, minus 1, comma, abs of y, 1. And this will give you a plot, you know, like this. Well, like in this example, this would give you a plot like this. This, okay? If you use that plot, that would be minus n over 2. This would be n over 2, and these would be all the values. So that's a very, very useful function, y1. I'll have more to say about it, or we'll talk about this later. The other thing you could do, but this is just points, minus n over 2 to n over 2. If you really wanted, this we know corresponds to minus pi, that corresponds to plus pi. If you really wanted to do a plot in terms of frequencies, and again, I will talk about this more later, what can you do? You could plot minus n over 2 to n over 2 minus 1 times f sub s. That's the, if you knew the sample frequency, n comma abs of y1. And as we will see later, this basically plots the spectrum in terms of real-life frequencies, assuming we've generated samples by sampling at some frequency. And if you have a real signal, so I'm just kind of a little bit ahead of ourselves, but you can, these will be reference notes. If you want to plot this stuff out, you can always remember these notes: 0 to n over 2 minus 1 times fs over n, comma, abs of y. That's without the FFT shift, 1 to n over 2. So anyway, a lot of different ways. I'll come back to this in a moment. But in any case, that's the end of my MATLAB aside. So I will scan that to make sure you should use that, you know, as a reference later on when you actually do plotting and so on. Okay. But we move on as usual. Okay, so that's a little bit about that. Okay, notes on analog or continuous versus discrete DFT frequencies. Okay, well, we've already seen with sampling that we can, if we're talking about continuous time, actual frequencies, then we typically talk in terms of hertz or in terms of radians per second. Either way you want to do it. And hertz is in units of, also called cycles per second, or hertz, okay? So radians per second, if we divide that by 2 pi, rads per second, we will get frequency in hertz. or cycles per second. Now, if for the DTFT, in our DTFT world, if we've sampled a waveform, we know that we deal with little omega frequencies in dimensionless in radians. And little omega over 2 pi, what's that going to equal to? Little omega over 2 pi is equal to, we know that if we've sampled this by the frequency domain version of the sampling theorem, that's the same as omega times t over 2 pi. And this is the same thing as f, omega over 2 pi is f, t is 1 over f sub s, and that is equal to our DTFT frequency. And that is dimensionless. I prefer to think of this instead of, well, it is dimensionless, but it's just a number, but I tend to think of it as cycles per sample. Okay? In the continuous world, that f had units of hertz, which are equivalent to cycles per second. I tend to think of this as cycles per sample. But in any event, it is a dimensionless number. Now, when we go to the into the DFT world, then things are a little bit different. There, omega sub k over 2 pi is equal to k over n. Why? Because omega k is 2 pi k over n, and 2 pi k over n, the 2 pi's cancel, and you're left with k over n. And now I think of this as equal to, remember in the discrete time world, omega over 2 pi we wrote as f over fs. Now in the DFT world, we're also dealing with omega k, and so this omega k is also equal to k times delta little omega. Delta omega is equal to 2 pi over n, see? So we can also write this as omega sub k. We can write this omega sub k as equal to omega sub k over 2 pi, I'm sorry, is equal to f sub k over f sub s. Okay, can do that. And substituting in for omega sub k equal k over n, we end up with this handy-dandy little formula. Omega sub k over 2 pi, we can write it as k times delta f divided by f sub s, where delta f denotes the frequency separation in actual hertz between the DFT frequencies. This doesn't apply if you have n data points. You just take a DFT. If you don't know where the data points, if you don't know if they were sampled or not, you don't know what the sample frequency is. But if you've sampled a waveform at a known sampling frequency, then those values you get out of the DFT, you can interpret those as actual frequencies. And each point you can interpret as k, as a normalized frequency, k times delta f over fs, where delta f is equal to fs over n. So you can see that by writing omega k over 2 pi as k over n, writing that as k times delta f over f sub s, and voila, you will find that delta f, which is the frequency spacing between the DFT cells, is just f sub s over n. So another way, and that's what I call the DFT's bin spacing, or in hertz, or in cycles per second. That's an actual honest-to-gosh frequency, hertz. And that's your minimum spacing between DFT. So the DFT provides the blurred and possibly alias samples of the DFT at these discrete intervals, frequency intervals, k delta f, where where delta f is fs over n. So, quick example, then we take a little break. Again, it's kind of a cartoon figure. I have better examples in a few minutes with with actual sine waves are much better examples. But anyway, here's again a picture I took. Suppose this were samples of an analog waveform. It could be an audio waveform. And I've sampled this with a 20 kilohertz A to D converter, so everything's very slow. This is audio. And I will assume that the maximum frequency in this audio signal is 9.5 kilohertz. So basically that means that's my F max, so there's no aliasing in this case. And I've just sketched out what might be these 100, and I take 100 samples, 0 to 99. So I've sketched out what might be those samples. Now I take a DFT, and let's suppose that the signal is kind of like a low-pass type spectrum. So what might my DFT look like if I plot the absolute value? If you just plot it out, you don't use this FFT shift or any of that, you're going to get stuff like this, see? Whatever. There might be some dips and stuff, but basically you'll get stuff looking like that. You'll get a 0 right in this region because this corresponds to the F max over 2 region. Okay, you'll get a 0 there because we said there's no aliasing, and you'll get it go up to here. And that's what it would look like. And the spacing between these little points in terms of real life frequencies turns out to be F sub s over n, which we can compute. F sub s is 20 kilohertz, that over 200 hertz. So that kind of corresponds to your, if you're trying to figure out some frequency feature, which is a lot smaller than 200 hertz, good luck. You're kind of stuck with this as the smallest separation you can get, 200 hertz. Wow. Where am I? Jesus. You know, you get talking, you don't realize. Screwed up your voices. I guess you guys realize that, don't you? Because you've had to listen to me go on. Okay, why don't we take a break, and I will see you in 15 minutes. Okay, so I will be back. Mr. Humes, Mr. Penn is not here. We'll put those back in the office. And I will see you in a few minutes. If I can stand up. Oh, man. I'm not a young man anymore.
guys make the R's like that? That's good, because look, permission does the same thing. Yeah. That's what permission does. He permission, he does the same thing. So he does see little R's, look. I was like, wow. I was just wondering, is that trades from the country, old country, or from your country? Or is that just, okay. Okay. So you've been here for 1 year in the United States? Or have you always been here?
No.
Are you international? Okay. So is it any different in coming here than it is where it is there? I mean, is there a culture change coming here, or is it? It is. Okay. I just want to say, but I won't take any more of your time. You're finding more. You got a break right now. But I do know some people. So I didn't ask you. I need to ask you right here. If you're going to do some. You said it was electrical engineering. Okay, so I'll write that down. Okay, I have a person that I know who's pretty good. She's down here. I think, and so you're in LA, so you're planning to stay here?
Yeah.
You're not planning, maybe ask you a question. Are you planning to, if you found a place out of state, would you go live there? If you find a job to work, but are you trying to do an internship, right? I mean, I'm not. Are you trying to do to be an intern? I mean, are you trying to do an internship at a company and then come back? I mean, you know, or yeah, I mean, like most people, when you won't start on the company, because I hear now that these guys are really, when it comes to looking for jobs, they're really putting a lot of pressure on people. Not to say that there's nothing wrong with that, but I noticed that it takes like 5 or 6 interviews before you finally get the job. I mean, it's not like it was. You just walk in, those days are over with. So you really have to, what I was saying, if someone got you to work somewhere else, somewhere further, I guess you would go there too. Yeah. Okay, well, my reason why I would say that, because there's a lot of times people have different locations where they're hiring or where they're from, you know what I'm saying? There's like consulting companies. How about consulting work?
I don't know. I mean, I just want to socialize for 2 months.
Okay. So not full-time, part-time? I mean, maybe I should ask you, are you coming back to school next semester?
Yeah.
Okay. So you're not going to plan to stay here. You're not a full-time?
No.
Okay. Okay.
Thank you. Can I actually get your contact?
Yes, I have a contact too. I'll send it to you right now.
Okay.
But my name is Carl. You put it in there. He's Carl. C-A-R-L. Mullins. M-U-L-L. Actually, yeah, Carl Mullins. M-U-L-L-I-N-S. That's my name. My telephone is 323-439-4396. Do you use LinkedIn? Have you set yourself up yet? Okay, so I can search for you right here, right now. I can do a search like this, right? And can I search for you right here if I do this? Okay, let me just do this. Okay, so if I did this, you are, no, you know what?
I actually searched for you in Google.
Okay, yeah, because see, look, here I am right here. I'm right here.
Okay, sure.
so much. I'm trying. I think that's pretty clear. Okay. Actually, we're doing pretty good, making progress. Yeah, I apologize about this kind of moving ahead here, but anyway, so that's kind of a note on the actual frequencies. So, like in this well, kind of an example, I guess. So, for instance, in this particular example, if you did we were just talking this before the break. If you did the DFT, you know, if it depends on, of course, what the spectrum, the continuous spectrum of x of n looked like. It could look like this, you know, kind of curly, or you know, it could have some peaks in it, etc. But we're assuming it is band limited to 9.5. So whatever it looks like, you would get samples of this, you know, at these frequencies. What are those frequencies? Those frequencies are multiples of the basic DFT frequency, the inherent resolution, which is delta f equal f sub s over n, which you derive directly from, really, from the frequency domain version of the sampling theorem and the condition of no aliasing. That's where you get these frequencies from. So those are the in this particular example, I chose n equal 100 samples. So you'll get 100 samples between here and here, and they will be separated by f sub s over n. In this case, that turned out to be 200 hertz. Okay, so that was our setup. We can equivalently relate the DFT spacing between bins. This fs over n. This is a good little trick to remember, or a little hint to remember, to the total time sampling interval. So in other words, if you collect, here's another way to think about it. Suppose you do a DFT using n samples, and when you multiply the samples times the time between samples, that's what I would call the total time duration of this segment of data. So if for instance, in this case, just take these examples, 100 samples at 20 kilohertz, how many seconds does that correspond to? Well, it corresponds to 100 divided by 20,000, or equivalently, it corresponds to that. Corresponds to 5 milliseconds. So in this case, I'll show you how I knew that so quickly, well, kind of quickly. So n divided by fs is equal to n times what I'm calling t, remember, is equal to 5 milliseconds, okay, in this particular case. 5 milliseconds. Well, if you compute this, the minimum spacing between the DFT points, that's also equal to 1 over delta f. So if you know you've collected 10 seconds of data and you've sampled it at whatever rate, and you have 1,000 samples, or 10 seconds divided by the sample rate, you have that many, or 10 seconds times the sample rate, and then somebody asks you what is the minimum spacing, this delta f, fs over n. Well, all you need to know is how long of a data segment you have. In seconds, take 1 over that, and that's your delta f. So that's another way to look at it. We can equivalently relate the DFT spacing, that delta f, fs over n, to the total sample interval nt, as delta f is 1 over what I'm calling t sub a, over the total sampling time interval, okay, or aperture, however you want to call it. Alternatively, we can relate the time sampling interval, t equal 1 over f sub s, to the DFT frequency spacing, the minimum spacing, as t equals 1 over n delta f. Okay, so or in other words, so this is n delta f, and that's equal to 1 over f sub s. Okay. Now the n delta f is the total span of the frequencies in the DFT. So here you're saying that the sampling interval can be related to 1 over the total span of the frequency, or equivalently you can say the minimum frequency spacing delta f is 1 over the total amount of data that you have in seconds. So that's it. If we increase n, but we keep the sampling interval 1 over fs or t, if we keep that constant, then we obtain more closely spaced DFT points. Why? Because delta f is equal to f sub s over n, which is equal to 1 over n times t. So I'm saying if we keep t constant and we increase n, then we shrink delta f. And ultimately, we will improve this blurring. We'll reduce blurring, I should say. If, on the other hand, we increase n, but we keep n times t constant, so we keep this constant, t sub a equals nt, keep that constant, but we keep increasing n, that means we're decreasing t, and as it turns out, we don't really change the resolution because you've kept nt or 1 over delta f the same. So anyway, there's a lot of games you can play, but the bottom line is this. The longer of span of time you can collect in seconds, finer the resolution of the DFT or FFT you'll be making. So that's some of the trades. That gives you some of the idea of how to interpret the frequencies coming out. And if you go back to my reference MATLAB, that'll show you how to interpret it by, well, we'll come back to that in a second. Okay, zero padding. Zero padding, what is it good for? Absolutely nothing. Say it again. No. Zero padding, what is it good for? Why would we want to? We already know what zero padding can do when we talked about the circular versus linear convolution, or the using the DFT, FFT for doing filtering in the time domain. But how can this zero padding, what does it do for us in terms of spectrum analysis? Okay? So the question is, what happens if we zero pad? So let's say we have 100 points, but I'm going to add 1,000 zeros on it, or 900 zeros. So I'm going to take my 100 points and turn it into a 1,000-point sequence, but I'll just have the 100 points and 900 zeros. Does that do anything for us? Does that help resolution? Anybody? Anything? Not anybody, I'm sorry. How does it help us? Well, we'll see. Let's take a look. The answer to that, by the way, even though you would think adding zeros can't help us, we don't learn any more about it. But it turns out there are cases where it really does help. So I'll come to that in a second. Okay, so what happens if we zero pad out to length? So first of all, let's look at the DFT, okay? And the DFT, yeah. So x sub p of n is our zero padded sequence, okay? Just like the x sub z's we talked about before. And we're zero padding it out to a total length of p samples. Now we're going to do a DFT. What does the DFT look like? It looks like this, okay? Summation n equals 0 to p minus 1 x sub p of n. Now, as it turns out, before, x sub p of k is going to equal to x sub w, that convolution I talked about, okay? It's going to equal to that convolution sampled at the frequency points omega equal 2 pi k over p. Now, the first thing you may ask yourself, wait a minute, time out. Is that the same x sub w that you had when you didn't add zeros? Yes, it is. It is the same x sub w. You know why? Because I can write x sub p of k is equal to, guess what? It equals 0 to n minus 1 x sub n. It's the same thing, either minus 2 pi j k n over p. Okay, I mean this don't let the sum fool you. It goes from 0 to p minus 1, but it's equivalent to the sum from 0 to n minus 1. In other words, these two sums are the same. Why? Because x sub p of n is 0 for as long as little n is greater than n, or greater than or equal to n. This x sub p of n is 0. So these two sums are the same, you see. And once you realize that, then you look at this and you ask yourself, now how can I relate that to this dtft? Well, this is simple. This is the same thing as x, just the same x sub w I defined before, which is a function of only the n samples of e to the j omega, evaluated at omega. So I haven't changed anything. Or have I? Where are the frequencies that I sample it at? Are those the same as before? No, they're not. They're equal to 2 pi k over p. And that's for k between p minus 1 and 0. So what zero padding does is you still got the same, quote, blurring. That you haven't changed because you only have n samples of data. But what the zero padding does is it lets you observe the frequency content of the DFT at much more closely spaced points in omega. And that can be useful. And I think I have an example. I probably don't. Well, I can't see my example, but if I don't have it, I'll get it next time. In any case, but that or maybe it's later on in the notes. But this actually, it turns out it can help a lot, which I will show you a little bit later on. So generally, x sub p of k, it's the same smearing function, but just at much more closely spaced points in frequency. So I have a little conclusion. The DFT of the zero padded sequence and the DFT of the original sequence represent the same envelope function, x sub, what I'm calling x sub w, which is just a function of n, not p, but sampled at different points along the unit circle. Thus, zero padding does not reduce the blurring. It only gives us a better picture of that blurring function. Now, you might say, well, how could that possibly help? It will help. It will help, especially when we talk about sine waves. So I guess I'll wait till I get to that point a little bit later on. Okay? So that's how it will help. Do I need to... Well, I had some notes. Well, I've already done that, so I don't need to show you that. Let's see. Okay. Okay, so let's so anyway, hopefully I kind of scribbled it in lining of the notes, but basically, where am I? 7, 8, 9. Oh, yeah. So anyway, that's the idea. If I zero pad my sum effectively over non-zero values of x of n, just as 0 to n minus 1. So that's why you get the same envelope function. But you do sample it at more closely spaced points in frequency. And I will show you, I'll give you a really good example of when this actually helps you a lot when I talk about sine waves. But I will come back to that. Okay, let me move on. So this is kind of a good place to sort of summarize where we're at. Review from last time. Well, this was last time. So this is kind of where we at. We started with the continuous time waveform, okay? And we took the infinitely long sequence, or infinitely long waveform in continuous time. We took the CFT of that. We assumed there was no aliasing, so we sampled this at some sample frequency f sub s without aliasing. We then took the dtft, that was x sub e to the j omega, and we also selected n points of this sample waveform and took the dft of that. And we related all of those together under the assumption of no aliasing. And we found this before, this is kind of where we're at. This is the DTFT in terms of the CFT. Yes, sir.
How do you sample DTFT to DFT?
I'm sorry, say what?
How do you sample DTFT to DFT?
You,
In order to get the DFT sequence, we have to sample the DTFT, right?
well, well, in a sense, I mean, the way I'm generating it is I'm just taking a subset, you know, n samples, and I'm computing the DFT of that. But yeah, we've related the DFT to kind of a smooth version of the DTFT at those discrete frequencies. Is that what you were?
Yeah, how do we select those discrete frequencies?
Well, you know what? I'll tell you how we select. This is the beauty of this DFT. They're selected for us. I mean, it's pretty much, that is the definition of the DFT. And I think, see those DFT frequencies? The question, what? No, I don't have that. I need the microphone again. Okay, so the question is, I guess your question was, well, let me make sure of this. Where do these frequencies come from? 0 less than or equal to k less than or equal to n minus 1. Is that what you're asking? Where do these, how do we select these frequencies? Well, these frequencies are basically, as I said, they're selected for us by definition. The DFT is x of k, this is the definition, n equals 0 to n minus 1 x of n times e to the minus 2 pi j k little n over n. So that's the definition. And this I can write as e to the minus j omega sub k, where the omega sub k is 2 pi k over n. So basically these frequencies fall right out of the DFT, the definition. Now you might ask, why is the DFT defined like this? But I think it has probably to do with the FFT algorithms that have been developed.
So what we do is, DTFT is defined from minus pi to pi.
Yes.
So we take n samples from that period interval minus pi to pi.
Now see, the DTFT is actually, it's really defined for all omega. It's just it's periodic, minus pi to pi, then pi to 3 pi, etc. What typically with the DTFT, since we're not restricted, we can pick any omega we want. We typically pick the omega between minus pi to pi. But when we do the DFT, we don't sample that interval in frequency. We sample the interval 0 to 2 pi. Now, because the DTFT is periodic, then we know that the frequencies from pi to 2 pi are the same as between minus pi and 0. So we haven't lost information. We just rearranged it in kind of a goofy manner, you know. We would hope that the DFT would sample the DTFT from minus pi, but it doesn't. It samples it from 0 to 2 pi. So it's all right. Whatever works, we'll use it. So hopefully that answered you. The reason why I'm double checking you asked a question last week. I forgot what it was, but I kind of glossed over it, and then when I realized what you were asking, then I saw what I had made a mistake in the notes. So now I'm listening to you carefully. But anyway, that's kind of why. It's just a definition, really. Okay, so that's what we learned. We learned that the DTFT was related to the DFT by this sampling in the frequency domain. But where this was not the DTFT, but it's a smooth version of the DTFT, which is basically defined by the convolution of the DTFT and the DTFT of this rectangular window function. So that's kind of where we're at. Like I said, it's a good time to summarize where we're at. And the window function, or I should say its transform, was what I call the sinc function. It looks like this. That distance there between the null and the null here is actually 4 pi over n. That we would call the main lobe width of that of the DTFT of the DTFT of the rectangular window function, and these levels here are called the side lobes. Okay, and it turns out the sine omega n over 2 divided by sine omega over 2, it has zeros at 2 pi over n, 4 pi over n, 6 pi over n, etc., etc. Okay, so that's sort of a summary of where we're at. DFT is a blurred and sampled version of the DTFT, and then we related the frequencies of the DFT and the DTFT. We related those frequencies to the actual input frequencies in hertz. Now, one thing I wanted to go into a little bit more depth here is that typically when we compute the DTFT, as I've been lecturing for all the lectures up to this point, we typically evaluate the DTFT from minus pi to pi, or in terms of sample frequency, from minus sample frequency over 2 to plus sample frequency over 2. And really, if the input or if the signal is real, then really all you need is just from 0 to fs over 2, because you know it'll be symmetric, kind of like this picture here. Okay, so that's where we have typically defined the DTFT from minus pi to pi. But as we now know, because of the way the DFT is structured, it evaluates frequencies not from minus pi to pi, but from 0 to 2 pi. Okay, omega sub k equal 2 pi k over n, and where k goes from 0 to n minus 1. So what to do? This in turn corresponds to the discrete analog frequencies fk equal omega k over 2 pi times fs equal k delta f, where delta f is equal to fs over n. So little omega sub k between 0 and pi, okay, that only corresponds to half the DFT index range. Okay, so let me say it again, kind of an important point. The interval omega sub k between 0 and pi, okay, which you really like is between minus pi to pi, or if it's real, from 0 to pi, that range from 0 to pi corresponds to the discrete index range in the DFT of the first half of the samples. Okay, so if we look at the samples from 0 to n over 2, that really maps to omega between 0 and pi. What about the other frequencies, minus pi to pi? Or equivalently, what about the other half of this DFT frequency range? Well, let's take a look. So indeed, how about that range from minus pi to 0? Okay, well, again, there are no negative indices in the DFT. That's how life is. No negative indices. But recall the periodicity properties of the DFT, okay? You may recall those. When we define the DFT, x of k, x of little n, e to the minus 2 pi j k n over n, big N, then I ask, or you can ask yourself the question, what if you replace k, the frequency index, with k plus big N? In other words, you evaluate it basically outside of the range. What happens? Well, you will find that x of k is periodic with period n. Namely, specifically, you'll find that if you computed this sum, the DFT sum, but you replace k with k plus or minus n, you just get x of k. Okay? So the DFT, the definition, this definition, it's certainly well defined for k values outside of the range 0 to n minus 1, but it turns out it is periodic outside of that range. Okay? So just keep that in mind. This is totally analogous to the DTFT. The DTFT is periodic, x of e to the j omega, periodic. I don't know if you can read this, and you know this already, but with 2 pi, periodic. Well, the DFT is periodic in n samples, see? Okay? So keep that one in mind. That can help us figure out our dilemma in terms of where did the negative frequency goes? Where do we get those? So the interval minus pi to 0, we knew where pi to 0 was. So the interval minus pi to 0 it's got to correspond to this the other half of the DFT indices, n over 2 less than or equal to k less than or equal to n minus 1. Why? Why do I say that? Well, let's take an example. X of n minus 1. Okay? So let's say k is n minus 1. Well, I know that's the same thing as x of minus 1. This is frequency omega equal to 2 pi n minus 1 over n. This is frequency omega equal to minus 2 pi over n. So by the periodicity nature of the DFT, or the 2 pi periodicity of the DTFT, frequencies near 2 pi are the same as frequencies at the at the low frequencies, at the small negative frequencies, I should say. So when you compute the DFT, you get the frequencies up near k equal n minus 1. Those actually map to the low negative frequencies. Okay. So if you ask the question, what happened to the frequencies between minus pi and 0? Well, they're there. 0, or actually negative minus 2 pi over n, that frequency's there. You haven't lost any information. That corresponds to the frequency cell n minus 1. What about the frequency minus pi? Guess what? That corresponds to this frequency, n over 2. So when you look at the last half of the array, it's a little convoluted, but 0 to n over 2, and again, I'm assuming for simplicity, n is even. 0 to n over 2 minus 1, okay, 0 to n over 2 minus 1, let me say it again, is, no, wait a minute. Where did I say that? Discrete frequencies. Oh, there. 0 to n, well, actually, yeah, 0 to, actually, this is n over 2 minus 1. Frequency 0 to n over 2 minus 1, that corresponds to the range of 0 to pi, okay? But if you want to know where the negative frequencies are, they're in the last half of the array, n over 2 to n minus 1, but not quite necessarily what you would imagine. You might think the n over 2 would be a small, no. The n over 2, that actually corresponds to minus pi. So you've basically jumped from pi, you've jumped from, sorry about this, you've jumped from pi to the very next point being minus pi because of the periodicity, 2 pi. So in any event, this range, n over 2 to n minus 1, the last half, those actually correspond to the negative frequency. Let me illustrate this. So omega sub minus k is equal to 2 pi minus k over n, corresponds to the range 0 to n over 2. Okay, so those are the negative frequencies. So omega sub minus 1, that DTFT frequency, would really be DFT frequency n minus k equal n minus 1. Omega sub minus 2, 2 pi minus 2 over n, the DTFT frequency, that would correspond to the DFT index n minus 2, and so on, all the way back. Follows directly from the periodicity. Look, let me give you an example. Here's a simple example. From now on, I will look at sine wave examples. They're the simplest to deal with. Let's say I give you a complex sine wave, okay, that you've sampled. X of n is e to the j omega naught n, and let's say that omega naught was in fact this minus 2 pi over n frequency, okay? So your sine wave is e to the minus 2 pi j little n over big N. Now let's do the DFT. And let's ask ourselves, what will the DFT look like? Well, here's the DFT. I've rewritten it like this, and n equals 0 to n minus 1 e to the minus 2 pi j times 1 plus k. n over n for values 0 to n minus 1. Now you might think, well, I know that when I take when I sum a sine wave from 0 to n minus 1, and the sine wave is frequency, some multiple of 1 over n, I know that I'm going to get 0. So when you first look at this, before you really think about what's going on, you might say, well, hell, this is 0. Where did my negative frequency go? I'm just getting zeros. But not really. It is 0 for k, for most of the k values. In fact, if you evaluate this, this is equal to 0 for 0 less than or equal to k, less than or equal to n minus 2. How can you prove that? Use the geometric sum formula. You'll see it's true. But what happens when k is equal to n minus 1? Remember, I just told you that a frequency at minus 2 pi over n will map into the DFT frequency, k equals minus n minus 1. So if that were true, then I would expect to see something non-zero when k is equal to n minus 1, corresponding to that sine wave at frequency minus 2 pi over n. Let's see if that's the case. Check it out. Suppose k were n minus 1. So 1 plus k would be n, capital N. Now, that's capital N, so that's going to cancel the n here. I'm trying to do this kind of just looking at it by inspection. So the n here, when you let k equal n minus 1, that'll be n. That'll cancel the n. You'll get e to the minus 2 pi j little n, sum n equals 0 to n minus 1. Guess what that will be? E to the minus 2 pi j times 10 is the same as e to the minus 2 pi j times 1, the same as e to the minus 2 pi j times 0. Namely, this will all be 1s. Okay? So when k is n minus 1, this 1 plus k will be an n. It'll cancel the n here, and you'll sum up a bunch of 1s. So here is the final result you will find. That the DFT of this sine wave will equal 0 for 0 less than or equal to k less than or equal to n minus 2, and it will only be non-zero when k is equal to n minus 1. So that is where the sine wave pops up. Here's another way of doing it more analytically using the geometric sum formula, but you get the same result. And this is what you would find. You can try it. You can use MATLAB and try it. If you take the DFT of e to the minus 2 pi j over n, you know what? The sine wave shows up over here. And what index is that? N minus 1. So when you interpret the DFT and you get these values, if I input a complex sine wave or a real sine wave, the negative frequencies will actually correspond toward the latter half of the DFT output array. So this impulse at n equal minus 1, which is what you would get, you can try it, physically corresponds to this picture. Okay? It physically corresponds to this picture, where you get, in terms of frequencies, this is, I would plot this, say, versus omega sub k. This is what you would get with if you did a DTFT and evaluate it between minus pi and pi. You get an impulse, a spike, at omega equal minus 2 pi over n, just like you would expect. So, to physically understand the DFT spectrum, okay, when you do a DFT spectrum, the first rule is before you do anything, use what I call the cut and paste operation, which in the MATLAB world is called the FFT shift, the old shift, like playing football. Anyway, you need to do, and I call it the cut and paste operation. And by that I mean you take the DFT bins from n over k equal n over 2 to n minus 1, and you paste those back to the bins from minus n over. Basically you move those from back to minus n over 2 to n from minus 1. But here's that. Let me use that same picture, if I can find it. If I can. Oh, wait a minute. Where was it? I screwed around before. Yeah, this is what I meant. So what I mean by that is, here's the DFT you would get. What I'm saying is, cut and paste. Take all these bins and just cut them, get rid of them, put them over here. If you do that, then you will have the correct interpretation of your DFT. Now again, if the input is real, what you will find is that these points, and that you could also see if you revisit the DFT symmetry properties, if x is real, these points, when we put them over here, they will be the exact replica of these points, see? But if for any reason x of n were complex, which it could easily be, then these points will generally be different. The DFT, the DTFT is not symmetric, the magnitude, if your input is complex, as you learned on the midterm, okay? So the first thing I encourage you to do before you do anything else, when you want to really interpret the DFT spectrally, is take these points and cut and paste them over here. And isn't it nice that the MATLAB has a routine that does that? FFT shift, okay? So that's where that routine comes into play. That's why MATLAB made it, so you don't have to do this by hand. So that's that. Also, we briefly discussed, well, zero padding from last time. And I just got done talking about that, so I didn't need to go back there. And I end up by saying, so all zero padding does is let you see the blurring effect created by the window at more closely spaced DFT points. Mark my words, that is not the whole story. I will show you the whole story later on. It does more than that, the zero padding. Yes?
You said, we discussed that the frequencies corresponding to the negative frequencies in DTFT are from n by 2 to n minus 1, right?
Yes, that is correct.
So where is the frequency corresponding to omega is equal to 0? Is it at the center of the sequence, the DFT sequence?
I don't know. No, I know. No, I'm sorry, I'm just messing with you. Now, the 0 is the very first point. So when you get your point, when you do your FFT, get your array, the way it'll work is at the very first point in that array, that will actually correspond to omega equals 0. The second point will be omega equal 2 pi over n, etc., until you get to the middle of the array. And then it depends on whether n is even or odd. But when you get to the middle, and then at that point, what will happen is that you will interpret, the correct interpretation is to take that and move it back. I mean, you're getting close to pi, so the next of the samples are greater than pi. You will invoke the 2 pi periodicity at that point. So the frequency at just greater than pi, subtract 2 pi from that, and that'll be the minus pi frequency. So it isn't, so it's weird how it works out, but the very first point is 0. The frequency just below that, minus 2 pi over n, that's the last point. And it makes sense if and only if you think about the periodicity of the DFT. 0, the same thing as n. So n minus 1 is very close to 0. So yeah, believe me, it takes a little bit of effort to get used to this DFT if you want to interpret what the frequency spectrum is with the DFT. Now, in these notes, I worked out, using the geometric sum formula, I worked out what the DFT of a sine wave would be in general, for a general frequency. So I have a sine wave. Now before, omega naught was minus 2 pi over. Now it's just omega naught is, omega naught, now I have a complex sine wave. Complex is useful to work with some omega naught between pi and minus pi, okay? So it's not necessarily 2 pi over n or 4 pi over n, it's just between minus pi and pi. But I'm going to compute an endpoint DFT of that. And the question is, what is the endpoint DFT going to look like? We're getting close to out of time. Okay. Well, there's two ways to do this. The hard way and the easy way. Well, the hard way, or the harder way, I should say, is by using, here's the DFT, the DFT is summation n equals 0 to n minus 1. So you can always use the geometric sum formula. N times e to the minus 2 pi j k n over n. So you can always, you can combine these two in one exponential, and you can ultimately use the geometric sum formula. That's what I did here. This is the geometric sum formula. That's what I call the harder way of doing this. And by the way, this geometric sum formula only works if, you know, that rectangular window, if you're using a rectangular window, okay? If you use any other type of window function, which generally we use, you can't even do the geometric sum formula, okay? But that's the hard way. There is a simpler way, and the simpler way is over here. Now this uses the result that we found before, namely relating the DFT to the blurred and sampled version of the DTFT. Okay, so let's start off with this formula. X sub k is equal to x sub e to the j omega combined with w, which is what I called x sub w evaluated 2 pi k over n. Now, what is x sub e to the j omega? Well, it's x of n is e to the j omega naught n. Now, we already learned that the DTFT between minus pi and pi was this Dirac delta function. Now, I don't know about some formulas, but I know this. I can convolve the Dirac delta function with anything. That I can do very simply. So let's take a look at what x convolved with w is. Well, substitute in the Dirac delta function, and you get, lo and behold, this. So in the case where you have sine waves, complex sine waves, and then if you had real sine waves, it's the sum of two sine waves, you can use linear. But here we're going to stick with complex sine waves. Then you find that x sub w, what is it equal to? It's equal to just w of e to the j omega minus omega naught. So in this case, and only in the case of complex sine waves, does this blurring function, this x sub w, this convolution function, it equals exactly, it traces out the frequency response of the window function centered at the frequency of the sine wave. Pretty simple. Can't get any simpler than that. Then ultimately you will sample that at omega sub k points. That is, and you say, geez, do you get the same answer that when you did this rigorous? Well, yep, same answer. And you know what else? You know what else with this approach? You get it for any window function. This doesn't, it's just in the case of the rectangular window function, is this the same thing? But this could be anything. Anything you multiply the input when you do your DFT with, different windows. This is very general. So I prefer this. This is the way. This is the easy way of computing the DFT with sine waves. And what did I do? Oh, well, now this will be pretty simple to see. So what I did was I said, let's take a special case, x of n equals, special example here, I will call this example, and this will be x of n equals e to the j omega naught n, where in this case omega naught is exactly equal to 2 pi over n. Okay? So what do you get when you get that? Well, it turns out if you do the DFT, remember I said when it was minus 2 pi over n, you got a spike at the end. When it's plus 2 pi over n, you do get a spike, and you get it right and in the second DFT output point. So if you did e to the j omega naught n, you can try it, generate n samples, do an n-point DFT with omega naught equal to 2 pi over n. You will find that when you look at the array, the first element in your DFT output array will be 0, the second will be non-zero, and then all the rest of the ones will be 0. What is going on? What is going on? Well, in this case, x of e to the j omega, no, I'm sorry. Let me do it this way. X of k is equal to W of e to the j omega minus omega naught. I'll just keep it as omega naught. Evaluated at omega equals 2 pi k over n. Well, what's happening here is that if you look at the magnitude of W of e to the j omega minus omega naught, well, first of all, if you recall, W of e to the j omega, if I just plotted that, it would look like this. You get a point here, and you get this, get this, get this. These are samples at 2 pi over n, okay? This is omega equals 0. This is 4 pi over n and so on. So now what happens if I were to sample this at omega equal 2 pi k over n? Well, you know what you'd get? You get this value, and then you get all the rest zeros. Think about that being shifted over. Instead of being at omega equals 0, it's omega 2 pi over n. It's going to be the same thing. If shifted over, you would have your non-zero value there, and then you'd have zeros here, here, and here. So if you want to think of it in terms of this simple formula, then you will see, yep, this is just tracing out, hello, this is just tracing out W of e to the j omega minus, I just dotted it for you so it'd be easier to see. This is your sinc function, see? This is your sinc function. I just moved it over, 2 pi over n, and look at that. There's your value. There's your zeros that you're sampling. So if you looked at this, you'd say, yeah, that's a sine wave, no problem. Now I'm going to play a game. I'm going to turn up the stakes. It's Emerald, but I'm going to kick it up a notch. Okay, so now I'm going to move this frequency off just a tad. I will move it off to 2 pi over n. See, it'd be nice if I moved it to 4 pi over n, because that's another DFT frequency. But nope, I'm not going to do that. Put it like this, see? 3 pi over n. Now what's going to happen? Well, see the dash curve? That's the sinc function for my window function in this case. Like this, see? But now it's going to be centered right here. But you know what? Sorry, there is no DFT frequency right there. Where are the DFT frequencies? They're here, and here, here, here. So instead of, you've moved the window function just enough so that instead of the nulls being at the sample point of the DFT frequencies, now the peaks, these little side lobe peaks are. So it's still a sine wave, but now does it look like a sine wave? Not really. This doesn't look anything like a sine wave.
Pardon me, Professor, 5 minutes.
Oh, okay, good. So that's what I'm saying. It doesn't even remotely resemble this nice single spike. Trying to think. Oh, okay. Well, I interpret it here on this page is in terms of the geometric sum formula. But the simplest way to interpret it is just what I showed you here. This is, think of it as W of e to the j omega minus omega naught sampled at the DFT points. And all you've done is you've moved that over to a non-DFT frequency, and now your samples don't occur at the nulls anymore. And that's the way to see it. Instead of seeing a sampled sinc function, and now we don't get a single spike, we get the sample sinc function for the window function. Sometimes people interpret this also as a leakage of power from the sine wave frequency, namely here, to all the other DFT frequencies. So that's another way to kind of intuitively think of it. When you take the DFT here, this is where the actual frequency of the sine wave is. Well, what happens because of the DFT frequencies, that they're not at 3 pi over n, they're multiples of 2 pi over n, it's like you take the power and you leak it all into all these other DFT frequencies. However you want to think about it, that's mathematically, that's physically what's going on. It's just a sampled sinc function for this window function. What if you had a different window function? Same thing, different window function, doesn't matter. what you would do is you trace out the window, the DFT of the window. Maybe it'd be broader, maybe it'd be more narrow. I don't know, but you would trace that out and then superimpose over that were the sample DFT frequencies, and that's how you interpret it. Okay, and then what I did was I did some different cases, and here was an interesting case where, not one of these cases. Oh yeah, in this case I zero padded from n to 2 endpoints. So these are some different cases. In this case, here I zero padded, and later on I will show you. Hey, wait a minute. Great. That's pretty much it. Okay, I got 2 seconds. That's pretty much everything I want to know about the DFT. I've defined what it is, told you about how to interpret it. Next time we're going to use it for an example from radar, okay? And later I will show you, and I haven't showed you yet, I will show you why zero padding can help a lot in terms of frequency estimation. So that's it. Thank you very much. I will see you all next week.